In this video, we're going to discuss complex conjugates, but before we do, we want to discuss what a conjugate is, how it works, and why we need them. So to work up to that, I want us to start by considering these two binomials, x plus 2 and x minus 2. Now, if I multiply these two binomials together, I need to FOIL. X times x, and I would get x squared. X times negative 2, I'd get negative 2x. Positive 2 times x, and I'd get positive 2x, or plus 2x. And positive 2 times negative 2 to get negative 4. Now, when I go about combining all of my like terms, notice negative 2x and positive 2x will cancel each other out. So we no longer have our x term. The only things we have are an x squared term and a constant term. So in essence, we were able to get rid of one term, or one kind of a term, using these two binomials. Okay. Similarly, I want to consider these two binomials, 3 plus the square root of 2 and 3 minus the square root of 2. So 3 times 3, we would get 9. 3 times negative square root of 2, we'd get minus 3 square roots of 2. Right here we have positive root 2 times 3 would make plus 3 root 2. And the square root of 2 times negative square root of 2 would be a negative square root of 4. This is one way to think of it. Square root, so just multiply these two together and get 4. Or you can also think of it as square root of 2 times the square root of 2. The square roots cancel, right? Because it's like we did square root of 2 squared. So if they cancel, this cancels out and just becomes 2. Just the constant 2. Again, like up here, we notice negative 3 root 2 and positive 3 root 2. Those are going to cancel each other out. So then, as we come down, we notice this just becomes 9 and minus 2. 9 minus 2 is just simply 7. Okay, so just like we did up here, we were able to eliminate some terms. In fact, we were able to eliminate a couple different terms here to get it down to just one constant, this positive 7. Okay, now let's see how that looks with complex numbers. So again, this I here and here, this is the square root of negative 1. So just like how this one had the square root of 2, this is the square root of negative 1. So it's going to work pretty much the exact same way. 7 times 7 becomes 49. 7 times negative 4i becomes negative 28i. 4i times 7 is positive 28i. Positive 4i times negative 4i becomes negative 16i squared. Just like we saw before, negative 28i cancels out with positive 28i. Now, this I squared becomes a negative 1. So 49 minus 16 times, not times I squared, times negative 1. And minus 16 times negative 1 is like saying minus a negative 16, which is plus 16. So we can get this to 65. So notice in all three of these, we were able to knock out some of our terms. We basically eliminated them. And the way we did it was you take the opposite of this piece. So instead of x plus 2, it's x minus 2. Notice that the x was not the negative version, just this piece, the 2 was. Same thing, to get rid of this square root, instead of plus square root of 2, we did minus square root of 2. Instead of plus 4i, this one had a minus 4i. So the complex conjugate is essentially just the imaginary piece. It's the exact opposite. So instead of plus 4i, it was minus 4i. If this was our original, it was 7 minus 4i. the complex conjugate would be 7 plus 4i. It's like basically just the opposite of the other one. So what are the complex conjugates of each of these complex numbers? So again, if you have the real part and the imaginary part, it's always just the opposite of the imaginary part. So for this one, it would be 2 minus 3i, right? The 2 stays the same. It's this sign that would change. For 4 minus 5i, it would then be 4 plus 5i. These would be complex conjugates of each other. If you just have simply negative 6i, this one might be kind of weird to think about. First, consider it 0 minus 6i, right? Negative 6i is the same as saying 0 minus 6i. Here's your real part. Here's your imaginary part. Now, to make this opposite, it would just be 0 plus 6i, which is the same as saying positive 6i. So these are complex conjugates of each other. So that'll cover it for complex conjugates.